What is up, young chemists? Mr. Rosen here. How's it going? Hope you're doing well. Today we're going to talk about electron configuration. The atom is made up of protons and neutrons in the nucleus, and in the space around the nucleus, you have electrons. Electrons fill space around the nucleus in what's called the electron cloud. A way to describe the possible location of some of the electrons in the space around the nucleus is called electron configuration. And at first it seems like a bunch of letters and numbers and exponents and kind of like gibberish, but with some practice, you'll see it's a regular repeating pattern, and you will be able to write electron configuration or see a configuration and know what element it is. So the first part of the video is going to be talking about electron configuration and explaining the what's called orbital filling order, the order that the electrons fill the space around the nucleus. So as always, you can pause the video and read what's on the page or replay it as I'm talking through it. So as I've said, electrons occupy the space around a nucleus. Okay, a description of the specific arrangement of the electrons in the space around the nucleus is called the electron configuration. Okay, now electrons occupy what are called orbitals, and orbitals are three-dimensional regions of space around the nucleus. So it's just like an area or a pocket of space around the nucleus. And the orbitals are located progressively farther and farther from the nucleus. In different regions of space around the nucleus. Now, the location of the orbital is, in terms of where it is relative to the nucleus, is primarily described using the principal energy level. So there's principal energy level 1, which is closest to the nucleus. Principal energy level 2, it's a little farther from the nucleus. Principal energy level 3 is even farther. So you're getting farther and farther from the nucleus, going to higher and higher energy levels. Each principal energy level has a corresponding number of sublevels, okay, and those we give letters, sublevel, and the letters are S, P, D, and F. The orbitals can have different shapes. We're not going to worry too much about the shapes, but regardless, each orbital can hold a maximum of 2 electrons. So that's an important concept. So if we are writing a description of the electron configuration, you have a large number, which is the principal energy level. You have a letter, which is the sublevel. And then this exponent is the number of electrons in that sublevel. And this is 1s1, but you can have an electron configuration that just keeps going. It would go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and it just keeps going, and you'll see the pattern. So as more and more electrons are added to the space around the nucleus, they fill the orbitals closest to the nucleus first, and then they move to higher and higher energy levels, getting farther and farther from the nucleus. And as I mentioned, each principal energy level has a corresponding number of sublevels. So you could think about this diagram here as, you could think about, like, let's say that the nucleus is right here. Okay, this is the nucleus. Principal energy level 1 is closest to the nucleus. And principal energy level 1 just has one sublevel, and that sublevel is S. So that's the 1s. Principal energy level 2 is farther from the nucleus, and it has 2 sublevels. It has an S, just like this, but there is also the 2p sublevel. And you can see that the P sublevel is larger than S because it has more orbitals. And that's just sort of another level of complexity here. The S sublevel has one orbital. Maybe I'll just jot this down over here. S is one orbital. And as we said above, an orbital can hold 2 electrons. So an S can hold a maximum of 2 electrons. P is 3 orbitals. If each orbital can hold 2 electrons, that means that a P sublevel can hold a maximum of 6 electrons. Principal energy level 3 is farther from the nucleus still. Again, we have 3s. We also have 3p, but then there is another sublevel, the d sublevel. So as we said, each principal energy level has a corresponding number of sublevels. A d sublevel has 5 orbitals. Each orbital can hold 2 electrons. So this can hold a maximum of 10 electrons in the d sublevel. And then going even farther out, we have principal energy level 4, where we have 4s, 4p, 4d, and finally 4f. Now, an f sublevel has 7 orbitals. And if each orbital can hold 2 electrons, that means that the f sublevel can hold a total of 14 electrons. Now, this diagram just stops here, but there is a 5th principal energy level, and a 6th, and a 7th. Those principal energy levels exist. In terms of the sublevels, we have S, P, D, and F. For we have S and P for the 7th. We have S, P, D for the 6th, and then we have S, P, D, and F for the 5th. So just in terms of the total number of elements on the periodic table, we don't have to worry about anything beyond an F sublevel. So let's bring it to the periodic table. Okay, let's make a connection here to the periodic table. So if you look at the periodic table, the sections on the periodic table correspond to both principal energy levels and sublevels. So this is period number 1, okay, and this is hydrogen. So period number 1 here, this is principal energy level number 1. So this is closest to the nucleus, right? So if you had a hydrogen atom, you would have the nucleus, and then you'd have 1 electron. It's as simple as it gets. And that 1 electron is going to get as close to the nucleus as possible, or as favorable. You then have, that's 1s, that would be 1s1, because you've put 1 electron. And then over here you have, still in the first principal energy level, helium. This would be 1s2. So this is the first electron you're adding. This is the second electron you're adding, because helium will have 2 electrons in the space around the nucleus. Now, if you want to add a 3rd electron, that next electron is going to be on the second principal energy level. Okay, now the reason why, going back to what we said above, principal energy level 1 has 1 sublevel, S. S has 1 orbital, and an orbital can only hold a maximum of 2 electrons. So for hydrogen, you have 1 electron, and then for helium, you have 2 electrons. Once you get to 2 electrons, that means that the 1s sublevel is filled. If you want to add another electron, it cannot go into this orbital. It has to go into the 2s orbital, which is at a higher principal energy level. Okay, so this would be 2s1, and then you could add another electron, and that would be 2s2, would take you right here. Now, once you're at 2s2, again, S can only hold 2 electrons. So if you want to add more electrons, it has to go in a different sublevel, 2p, right? The second principal energy level has two sublevels, S and P, and the S is already filled. So then you have P. P has 3 orbitals, which means it can hold 6 electrons. And if you look on here, this would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Once you get to 6, it's filled. And then you are here, which is the third principal energy level. So you start closest to the nucleus with 1s, and you add electrons one by one until the sublevel fills. And then you go to the next sublevel, or if needed, you go to the next principal energy level. And this is going to work like you read a book in English. You go left to right, top to bottom. 1 electron added at a time. So if you just took your pencil and went like this, and then like this, and then like this, and then like this, that would be the orbital filling order. Okay? And if we were writing out the electron configuration, you write out the filled sublevels. So let's do some practice. Let's start to get the hang of things, and you'll see this regular repeating pattern for writing an electron configuration. So we're going to practice going from the element to electron configuration, and then we're also going to practice going from the electron configuration to the element. So if you want to pause and do some of these, you're welcome to, and I'm going to go over the answers in just a moment. So these first 6 are the first 6 elements on the periodic table. So hydrogen is element number 1. So we start by saying, okay, principal energy level 1, it has 1 sublevel, S, and hydrogen is element number 1, which means it has just 1 electron. So 1 electron is going to go into that orbital. That's it. That's the whole electron configuration. You have 1 electron in the 1s orbital. That's it. Now helium is element number 2. I'm going to just number these. 1, 2, 3, 4, 5, 6. Okay? Those are their atomic numbers. That's also the same as the number of electrons that they have, because they're neutral atoms. The number of electrons equals the number of protons. So helium has 2 electrons. The 1s can hold 2 electrons. So instead of having just 1 electron in it, you're adding an additional electron, which is 2. So the 1s sublevel has 2 electrons. Now this means it's a full principal energy level. So if you want to add, lithium has 3 electrons. You're going to have 2 of the electrons in the 1s sublevel, and then it's full. If you want to add more electrons, it has to go to the next principal energy level, which is principal energy level 2. And in the 2s, you're going to have 1 electron. So these 2 electrons are closest to the nucleus. These are, or this 1 is farther out from the nucleus. This is the electron configuration for lithium. Okay, now beryllium has 4 electrons, so it's also going to be 1s2, and then you're going to have 2s. But instead of just having 1 electron in the 2s, you're going to have 2 electrons in the 2s. And hopefully you start to recognize that these exponents represent electrons, right? So hydrogen has 1 electron. So this 1 is how many electrons it has. Helium has 2 electrons. If you look at its configuration, it has 2. Lithium has 3 electrons. If you look at the exponents, 2 plus 1 is 3. Here, beryllium has 4. If you look at this, 2 of the electrons are in the 1s, and the other 2 are in the 2s. So 2 and 2 is 4. Now we get to boron. 1s2, that's filled. 2s2, and at that point, this is the same as boron. Sorry, this is the same as beryllium above, right? And if we're looking on the periodic table, 1s1, 1s2, okay, so that's filled. 2s2 is right here. And right here on the periodic table, this would be 2s2. Guess what's there? Beryllium. If you want to go to boron, this is the beginning of 2p, and you would just have 1 electron there. So you have 2p1. Again, look at the exponents. 2 plus 2 is 4 plus 1 is 5. 5 electrons. There we are. If you want to go to carbon, it's the same thing. 1s2, 2s2, 2p. All right, we're going to be in the 2p because this section of the periodic table, this is the 2p section. This was 2p1. If we want to add another electron, this is 2p2. And look, 2 plus 2 plus 2 is 6. And you could just keep going like that, right? We just went from element 1 to 2 to 3 to 4 to 5 to 6, and you just keep going, adding electrons until the sublevel's filled, and then you go on to either the next sublevel or a higher principal energy level. And you work your way through the periodic table, right? We just did these first 6 elements, which takes us to right here. Carbon is 2p2, 2p3, 2p4, 2p5, 2p6 would get us to neon. And then, P can only hold 6. So if you wanted to add another electron, we're at 3s. 3s1, 3s2, and then 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, and then we're at 4s, and you just keep going. This is the orbital filling order. You'll notice that the 2 columns on the left make up the s. The 6 columns here on the right are p. There are 10 columns in the middle of the periodic table. That corresponds to the 10 elements that can fit in the D sublevel. And also, down at the very bottom are lanthanides and actinides. There are 14 columns here, and that's because these are the F sublevels, which have 7 orbitals and can hold a total of 14 electrons. So you'll see the arrangement of the periodic table, the orbitals, it is not random. There are sections, S, P, D, and F. Okay, let's do some additional practice problems. If you want to pause the video, you are welcome to, and we're going to do these 5 next. Okay, give them a shot. Okay, so number 1 is silicon. First thing to do is find it on the periodic table. It's number 14. And you could get an idea, like looking at this, you could recognize, oh, this is 2p, and this would be 3p. This would be 3p1, this would be 3p2. And you can know, okay, the electron configuration is going to end at 3p2. And that's true. And the filling order is going to be the same as the other ones all the way up until that point, right? You notice it's the same filling order every time. You're just adding 1 more electron on. So we're going to go 1s2, 2s2, 2p. Now, we only went up to 6 last time, but 2p6, right? And if you want to, you can count the electrons. 2 plus 2 is 4, plus 6 is 10. So this has 10 electrons. And on the periodic table, this number 10, neon, has 10 electrons. And this is 2p1, 2, 3, 4, 5, 6. This is 2p6. So what we have here, This is the electron configuration for neon, right? This is 2p6, and it has 10 electrons, and this is number 10. So we need to keep going. After 2p, right? After 2p, if we're looking at this one, after 2p, we have 3s, and s can hold a maximum of 2. So we say 3s2. That has 12 electrons. Okay, so that is the electron configuration for element number 12, magnesium. And if you look, okay, this is 1s, this is 2s, this is 3s, 3s1, 3s2. And then we get over here to 3p, and we have 3p1, 3p2, which is where we end. 3p2. Now, if you look at the exponents, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus another 2 is 14. So this has 14 electrons. Silicon is element number 14. It has 14 electrons. And if you look at where it ends, 3p2, this is 2p, this is 3p, right? That's 3p1, that's 3p2. That's where we end. This is our electron configuration. Okay, now the next one on there, calcium, is element number 20. So hopefully you're starting to recognize, okay, this is 1s, this is 2s, this is 3s, this is going to be 4s, right? 4s, and this would be 4s1, this would be 4s2. Looking on the periodic table, or the diagram we have earlier, this is 4s, 4s2 is right here, and that's where calcium is on the periodic table. So it's going to end at 4s2. And the filling order is going to be the exact same as we just did here. It's the same filling order every time. 1s2, 2s2, 2p6, 3s2, 3p. Now, instead of stopping at 3p2, okay, right here was 3p2, we have 3p3, 3p4, 3p5, 3p6. So if we write 3p6, that has 18 electrons. This is the configuration of argon, but we need to go 2 more. So we have to go 4s2. Now again, you can check this. If you count these up, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20. This thing has 20 electrons. Calcium is element number 20. It has 20 electrons. And if you look at where it ends, 4s2 on the periodic table, 4s is right here. This is 4s1, which is potassium, and this is 4s2, which is calcium. And right there on the periodic table is where you find calcium. So we're going to get to some bigger elements now. Nickel is next. Nickel is a little bit further along in the periodic table. Here's calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. So it's number 28. So we're going to do all, 1, 2, 3, 4, 5, 6. So we're going to do the same filling all the way over. This takes us to 4s2, which is where we were before. So I'm going to write this exact same configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, so I have rewritten the same configuration. That takes us up to calcium. Okay, now, what comes after 4s2? Because s can only hold 2 electrons. After 4s2, we have the 3d sublevel. And I know it's a little bit weird because this is principal energy level 3, and it's coming after 4. And once you get here, once you get to 4, your D sublevel of a lower principal energy level occurs. So the S sublevel of a higher principal energy level occurs before the D sublevel of a lower principal energy level. So that's the orbitals start filling out of order, if you will, but the energy values between these two are very similar, very close. So this is 3D. So we're going to say 3D, and then we have to count over how many we have. So this would be, this is 4s1, 4s2, and this is 3d. So 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8. So 8 is where we're going to end this. And this, if you count these up, that's 28 electrons. Continuing along, niobium. It's not nickel, it's niobium, number 41. So we're going to fill, not just going to end at 3d8, we're going to go 3d10, and then this would be 4, right? This was 2p, this is 3p, this section is going to be 4p. And so we're going to fill that and then keep going. So we're just doing larger and larger electron configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now this time the 3d sublevel is going to be filled. Okay, 3d is filled. After 3d, right? After 3d, you have 4p, which can hold 6. After 4p6, you have 5s, which can hold 2. And then you have 4d, and we have to count over 4d1, 4d2, 4d3, how many we have to go over. If you're looking on here, this is 4d1, this is 4d2, this is 4d3. So we have 3 in the 4d. So it's 4d3. Sorry about the messages that are coming in. I cannot do anything about that right now. So if you wanted to add up all the exponents, at this point it's getting pretty big, but this takes you to 20, and then this takes you to 30, 36, 38, 41. Okay, 41 electrons. And niobium is element number 41. So just as a final one on here, xenon. Xenon is right here. And it's 54. Hopefully you recognize this is 2p, this is 3p, this is 4p, this is 5p. And you can see it's at the very end. So that means that the electron configuration is going to end at 5p6. So we're going to go all the way until 5p6. So we're going to go through the same filling order as we have been all the way out to 5p6 right here. So it is the same filling order, but even further. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Now this time the 4d sublevel is going to be filled, so 4d10, and then after 4d, right? After 4d, we get into 5p, and we're going 5p, 1, 2, 3, 4, 5, 6, which is where we're ending, 5p6. 5p6 is where we end. That's where our element is. If you want to add up all these exponents, this is 30, 36, 38, 48, 54. This is element 54, and if you look on the periodic table, it is 54. These are the correct electron configurations. So hopefully you see it's just the same repeating pattern until you get to the element, right? You're filling the sublevels up orbital by orbital until you get to the highest principal energy level and the sublevel that has that number of electrons. We're going to do a little practice going the opposite direction here. So here at the bottom of the page we have 3 where you're given electron configurations and you have to say what element they are. Again, if you'd like to pause the video, that's fine. I'm about to go over the answers. Okay, so there's a couple different ways you can do this. One way to do it is to just count the exponents, right? When it's this small, 2 plus 2 is 4, plus 5 is 9. So this thing has 9 electrons, right? 9 electrons. If it has 9 electrons, you can just look on the periodic table and see what element is number 9. Fluorine. So this is fluorine. Okay, that's pretty easy. But you could also look at the end of it. 2p, 5. You know that this is 2p, right? This is 2p1, 2p2, 2p3, 2p4, 2p5. It ends at 2p5, so you get to fluorine, right? Same with this thing. If you just already look at this and you go, I don't want to add all those up. 4p2, look at the end of it, 4p2. On the table, knowing the sections, this is 2p, this is 3p, and then this is 4p, right? This is 4p. It says 4p2. That's 4p1, that's 4p2. Germanium. Ge. Now, if you want to, you can add these up. 2 plus 2 is 4, plus 6 is 10, 12, 18, 20, 32. 32 electrons. What element is germanium? You guessed it, 32. So you can go forwards and backwards with these. Same thing here. This one, 5s, 4d6. Okay, so on our periodic table, this middle part is the D block. Okay, this is 3d, this is 4d. Okay, this is 1s, 2s, 3s, 4s, 5s. So this is 5s and then 4d. This electron configuration ends with 5s and then 4d6. So this is 5s and this is 4d, 1, 2, 3, 4, 5, 6. Ruthenium. So that's element number 44. Ru. And again, if you wanted to add these up, that's 36, 38, 44. 44 electrons. This element is number 44. We have a couple more of that style of problem right here. They're a little bit longer. If you want to try these, 4 and 5 here at the top of the page, go ahead. And then we're going to do a little bit of shorthand notation, and we'll finish up. Okay, pause the video and do these if you haven't already. But looking at this, it goes, all the way out, 5s, 4d, 5p6, and then 6s1. Now, in terms of the p sublevel here, this is 2p, this is 3p, this is 4p, and this is 5p. Now, if it says 5p6, Xenon is 5p6. So 5p6 is here. It then goes to 6s1. So that means we have one more electron than Xenon. That's element 55. And if we go over to this side, here we have element 55. And sure enough, in terms of our s's, 1s, 2s, 3s, 4s, 5s, this is 6s. And we just have 1 in 6s. So it's cesium, Cs. And again, if you want to count up all your exponents, you'll see that you do, in fact, get 55. Now this one, it ends in 4F3. So 6S2, let's see if I can, I don't know if I can fit this without zooming out. Okay, so 6S2, this is 6S1, this is 6S2. We then go into the 4D, and then, this is 5D, and then this is 4F. This is 4F. The lanthanides are 4F. So if it ends with 4f3, this is going to be well, this periodic table is actually going to be looking different than your periodic table. If we're numbering this as 5d1, then your 4f3 is going to be 4f1, 2, 3. Shoot. This is a little confusing because the periodic table I have is different than the periodic table you have. The answer for that should be neodymium and D on your periodic table. Hopefully it's a little bit closer or a little bit clearer. I would also just say that in terms of testing, you're not going to be tested on the F sublevels, so don't worry about that if you're stressed. You won't be tested on it, but you should know where the lanthanides and actinides are. Okay. This is obviously tedious. If I asked you to write this electron configuration out, you would say, okay, 1s2, 2s2, and you probably felt like it was getting tedious even when we were doing it over here, right? Well, there is a shorthand notation for electron configuration. And the shorthand notation is done by just using the noble gases as placeholders. So the noble gases are here on the far right side of the periodic table. And whenever you hit a noble gas, you have filled that principal energy level, and whatever comes next is going to be at a higher principal energy level. So, for example, if you get to argon, right, that's 3p6. If you wanted to add one more electron, it's going to be 4s, which is a higher principal energy level. Or if you got to krypton, right, this is 4p6, and you wanted to add one more, it would go into 5s. 5 is a higher principal energy level. So anytime you hit a noble gas, if you add more electrons to it, it's going to be at a higher principal energy level. So you can use these as sort of a placeholder, where you would just say the previous noble gas and then whatever comes after it. So, for example, radium. Okay. Radium is here, and if you look at the previous noble gas, so going backwards, this is 88, 87. The previous noble gas here, 86. Scoot this over. The previous noble gas is number 86. So if you want to write the shorthand notation, you would put the previous noble gas in square brackets. So I'm going to put Rn in square brackets. And then I'm going to write whatever comes after that. So after this, which this is 2, 3, 4, 5, this is 6p6. So whatever comes next, this is 7s, that would be 7s1, 7s2. You would write 7s2. That's the configuration shorthand for radium. This Rn in square brackets is the same as if you wrote out the whole configuration all the way past this to 6p6, right? This saves you from writing all the way to 6p6, and you just have to, by seeing Rn in square brackets, you know that the configuration is the same as all the way up to that 86th element. And then you just have whatever else. So niobium was an element we did earlier. If I wanted to do the shorthand notation for that, the previous noble gas, I would go back. This is 37. The previous noble gas is here, krypton, number 36. This is 2p6, 3p6, 4p6. So Kr takes us to 4p6. So I'd write Kr in square brackets. So writing that saves us from writing the configuration all the way to 4p6. And then what comes after 4p6, right, what's still left after 4p6 is 5s2, 4d1, 1, 2, 3. So we have 5s2, 4d3. So compare, this is our shorthand notation to our full notation. Here's our shorthand notation, and here is our full notation. So notice that right there, see where it says 4p6? That's the configuration of krypton. And what comes after krypton is this. So by writing Kr in square brackets, we saved ourselves from having to write all of that, right? That is krypton. We replaced that with this. And then you have what's left, right? Which is just this part. Hopefully you see how that works. Okay. Final one, arsenic. Arsenic on the periodic table is number 33, right here, 33. And you can see this is 2p, 3p, 4p3 is where it's going to end. But the previous noble gas, we have to go backwards, backwards, backwards. Okay, and just to keep going, back, 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 back. The previous noble gas is actually argon, which is 18. So we're going to write Ar, and then we have to write everything after that. So there's actually still a bit to write, because after argon, you have 4s2, 3d10, and then 4p, 1, 2, 3. So we have 4s2, 3d10, 4p3. So that saved us having to write, all of argon, but we still had to write a little bit afterwards. So this is shorthand notation. Sometimes it saves you a lot, right? This saved us having to write all the way out to element 86. Sometimes it doesn't save you too much, but it's better than nothing. Anyhow, electron configuration is definitely a topic where you have to just practice, 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 and you will eventually just sort of start to internalize the orbital filling order, and you'll start to get the hang of this repeating pattern and the places on the periodic table where you find each principal energy level and sublevel. Okay, make sure you study the sublevels, how many orbitals they have, and thus how many electrons can go in them, and really practice makes perfect. Do the ones in our packet, do additional searches online. The more electron configuration problems you can do, the better off you are. This is Mr. Rosen. Keep up the good work. Stay healthy, stay happy. I am out.